In this video, I'll talk about a couple of most common fragmentations of alcohols that would happen in mass spectroscopy. Alcohols typically undergo two most common type of fragmentations, and that doesn't mean it does not do any other sort of fragmentation, but these are the two most common fragmentations you would see. So suppose I have this alcohol here, and when I go ahead and create a um, radical cation out of it, the radical cation would look like pretty much the same thing with one less electron, because you lose an electron that makes the radical and also gets the positive charge on that oxygen, and also you have lost electron. So the molar mass of the radical cation and the molecule itself is not going to change because the mass of electron is a lot less. So the M over Z here is going to be whatever the molar mass is going to be for C6H14 and O. And this comes out to be, okay, 72 coming from carbons, 14 coming from hydrogens, and 16 coming from this oxygen. So that's going to be 86 plus another 16. That's 102. So M over Z is going to be 102. Now, this is another problem with an alcohol. It's very hard to see the actual molar mass of the alcohol. So it should have been somewhere right here, but I don't really have anything on this spot here. And that's because alcohols are not that fairly stable, and as a result, they actually undergo something called a loss of water as one of the type of fragmentation. So typically what I'm going to be seeing here is I'll lose the water here as one of my types of fragmentations there as a dehydration reaction. So when this undergoes in a dehydration, it makes a radical cation again, and that radical cation would actually have a double bond, and that would have one electron left when you do count all the electrons and whatnot, and it would have a plus charge left behind in there. So where that exactly going to be, that's hard to tell, because it's going to be either that carbon or that carbon, depending on who got less. But overall molecule would have one radical left in there, and then you would have a positive charge. So the actual molar mass of this compound was 102. You lose water, so that's not gonna show up in mass spec. So you're losing 18 here, so that means 102 minus 18 should give you about 84. So I should be seeing a signal at 84. So let's see if we have that, and we do have a signal at 84. So this is because of the alkene radical cation that you make after losing water. So that's one of the most common fragmentations alcohols do. The other common fragmentations alcohols do is obviously the the bond that's going to be broken between the carbon that's containing the alcohol or the OH group and the next door carbon. So let's talk about that. So suppose I'm looking at this guy right there. I'm just going to go ahead and copy the molar mass as well. So I'll have two possibilities where if I do go ahead and break it right here, so when I go ahead and break it right there, I would make the left carbon that's just going to be CH3. That would be in a radical because the carbocation of the CH3 is not going to be that stable. And I'll end up making this radical here, this cation here rather. So I would have, can say like one electron goes right here, one electron goes right here, and then one of the electrons from that comes down here to make the double bond there. So I will have a carbon here with 5 carbons rather, and then I would have a double bond. So I'm going to just kind of draw it like that, an H and a red, 2 electrons there with a positive charge. So that would be the radical that would not show up in the mass spec, and that would be the carbocation. And this carbocation is stable because it can also make another resonance structure where I can have this bond kind of coming going onto the oxygen and having the positive charge on this carbon. But here I'm going to draw the most stable one because this has all octets completed. So what I'm really losing here, so I'm starting out with an 102 molar mass. I lose in a CH3 radical, which is going to make an a 15 molar mass. So that means this guy right here, the carbocation that you made here, this is also called oxonium ion. And that would be 102 minus 15, so that would be 87. Let's see if we have anything at 87. You do have a signal at 87, so that kind of takes care of that problem. So this is because of the loss of CH3 radical. So sometimes they ask you, okay, how am I really getting this? And that's because of the loss of CH3 radical. And sometimes they would ask you to, can you go ahead and draw the fragmentation that would be coming from the 87 molar mass? And the fragmentation of that 87 molar mass would actually be this guy right there. All right, so that's what you want to kind of draw in that case. But that's still not really the base peak. The base peak is at 45, so let's just see what else we can do here. The fragmentation, just like we did on the left side, we can also do that on the right side. So let's talk about that. If I go ahead and fragment this right here, what I get this guy right here. Okay, I'm gonna draw the most stable carbocation here, and I'm gonna get a radical here, which is gonna be this guy. So the radical here would be C4H9, so that would be actually 57. So that means this guy should have been 102 minus 57, and you can do the math here, or you can be just like, all right, I got C3, C2H 5 and an oxygen there. Basically, I got 3 hydrogens here, 1 hydrogen here, 1 hydrogen here, so that's 5 hydrogens. So C2, that's 24. 5 plus 5, that's 29, plus oxygen, which is 16, that's going to give you 45. And you can just double check the math here. 5 plus 7, that's 2 or 12, and then 5 plus 4, that's 9, plus 1 is 10. So that is going to end up being the math here. So that's 45 should be your another signal coming from that oxonium ion, carbocation. And let's just see if we have anything at 45. And we actually do have a base peak at 45. So the base peak that you're getting here is because of that, you can call that an alpha cleavage type, where you're breaking the bond between the carbon that's containing or that's connected to the oxygen and the next door carbon. And in this case, this would look like CH3, CH, and then I got a double bond and an OH there. So that would be your fragmentation right there.